Okay, why don't we get started? Glenn's going to talk to us today about something he's been talking a lot about, the betting interpretation, the language of betting as a strategy for communicating statistical results.
Yes, I gave this talk. This is the third time I get it at Rutgers, right? It's evolved because I'm learning so much. I gave it to Doron Zauberger's scenario in math, and then I gave it to the stat department last week. So Harry and Robin have both seen it once before. But I hope this version is better. Anyway, this talk comes out of two things. One, of course, is the new book that I like to write about that Rolf and I published on Game-Theoretic Foundations. And the second thing is all this worry about the misinterpretation of p-values and statistical testing. And I imagine that you've all heard about this in one way or another. So there's a lot of p-hacking going on. People talk about p-hacking, where you just do a lot of experiments, do a lot of tests, and you get one that's significant. And if you do 100 tests, and you get something that only happened once in 20 times, and you get it published, that may not mean too much. And in recent years, people have been pointing out that a lot of the supposedly significant results you get back don't mean very much. They can't be replicated, etc. This is not there's a lot been written about this. One thing that amuses me is that people think that sort of the way we use p-values is the result of sort of Fisher, R.A. Fisher, and Jerzy Neyman, and the statisticians of the 20th century producing a bad theory. But in fact, these problems go back to the 19th century. And Joseph Fourier, the famous mathematician who did the heat equation, worked for the census, and he published a table of significance levels in 1826. And already by 1843, Cournot was complaining about the abuse of them, about this problem of people doing multiple tests. So I have a working paper that I'm about to post. I'd be glad to share it with anybody that's interested. We've got a hard copy here. I haven't posted it on our website yet, but because I'm still intensely working on it, and I'll probably do so in the next few days. The reason I want to give this talk is to get your feedback and to improve it. Well, and also to tell you about the ideas, which I'm kind of excited about. They come out of our book, but they're more about the application of the ideas to statistics. And I believe they're also relevant to the application of the ideas to the philosophy of science. And I'd like to say something about that too. But my focus is going to be on I'll try to get across the idea about the application of testing. Now, what I put up here is, you probably at least read the title there, that because of all the discussion about p-values, in the last few years people have been doing surveys about whether people really understand p-values. So they have these lists of questions. Here's two examples of surveys that have been given to a lot of people. And they have statements about what a p-value means. Something comes out statistically significant. What does that prove? Here's one way it's formed, one survey that's been used. Here's another survey that's been used. What they do is they list a bunch of false statements about p-values. P-value means this, it means that, it means this, it proves this, it establishes that. All the statements are false. In both the surveys, all the statements are false.
So H0 is true, is it not?
Pardon? None of the above is true.
Since they're all ridiculous, and then you put in something more ridiculous.
None of the above is. The only thing true here, the only true choice is none of the above. And none of these are true. So you give these to students. I mean, actually, I did this at the beginning. I'm teaching 2 courses this semester, and I did this for my students in my courses, graduate students and undergraduates. Graduate students in my course, undergraduates in the other. Nobody got all this right. Nobody got it. Everybody said something that was false. Well, okay, those are students. But the most dispiriting thing is you give these to people who teach statistics. They also get it wrong. You give it to people who publish statistics in social science or medicine. Most of them get it wrong.
No Bayesian would get it wrong.
No? But these people are Bayesians, no.
Why not?
People that teach statistics.
Why wouldn't a Bayesian get it wrong?
I don't know.
Well, the Bayesian wouldn't think that he could conclude that the hypothesis is false. Couldn't conclude it's probably false because it depends on its prior probability.
Anyway.
So that's what they would conclude.
No. I mean, if in fact the prior probability was sufficiently at a certain value, they might conclude that it's probably false. But it depends on that.
So but who's a Bayesian? There's probably 1 million people a year being taught statistical testing in the United States. 1 million a year. None of them are being taught Bayesian. I mean, a negligible number are being taught Bayesian. I taught last semester, I taught on this campus, a group of history and statistics to a group of seniors. They had never heard of Bayesian inference. They didn't know what I was talking about. I wanted to teach them the history about the thing. So, we could discuss the reasons why Bayesian is, off here in the clouds, and why nobody's teaching it here or studying this statistical testing. But there is a practical challenge of addressing, of trying to improve this situation. So, we had Andy Gelman came and gave a talk to us in the seminar last year, statistician at Columbia. So he and his friend John Carlin, and I don't remember who John Carlin, he's Australian, I think. He and John Carlin have a nice paper called Some Natural Solutions to the P-Value Communication Problem. So this is called the P-Value Communication Problem. The American Statistical Association put out an official statement. Here are misunderstandings of p-values, and we need to do a better explanation, a better job of explaining them. And Gelman, who is a Bayesian, and Carlin, I guess he's a Bayesian too, but anyway, they wrote a paper, The Natural Solution to the Problem and Why They Won't Work. So one of the solutions is to use Bayes. They don't think they're Bayesians, they don't think. Another solution is to just explain it better. We've been trying to do it for 150 years, explain it better. Confidence intervals in a test, practical instead of statistical significance. Anyway, it's a nice, I found it a really convincing paper why this problem is not going to get any better by...
Why do they say getting everybody to be Bayesians would work? Just couldn't get everybody to be stubborn?
Can I give another seminar on that? I have a different recommendation here that's not Bayesian.
Sure.
So I want to explain that. But I think, I do believe that the Bayesian cannot be sold to this audience, people that actually do statistical work at this level. They don't want to hear the subjectivity. What I'm going to introduce has a subjectivity too, but it's a little different way. So what's the idea? So I'm going to quote Gelman. He says he thinks a solution is that we have to get people to accept uncertainty. So all these mistakes, basically, one way or another, all these things that people are wanting to say yes to is because they want to give this p-value more meaning than it has. And of course, it has very little meaning when you get down to it. So Gelman says we've got to learn to accept greater acceptance of uncertainty. And of course, he is a Bayesian, so when he says greater acceptance of uncertainty and embracing a variation, he means make things more complicated. Make more complicated models with enough Bayesian set of probabilities and parameters. And, well, that's not convincing to me either because it just makes it so complicated. So I have something that's simpler that comes out of this game-theoretic point of view. And that is to go back to betting. One of the curious things about probability theory is that everybody knows it's about betting, but we keep it but we hide it. when you actually look at what's taught to statistics, there's sort of things that are really bets that we suppress the fact that they're bets. We hide that. And I'm saying if we want people to recognize that things are uncertain, we can do that by being candid that we're talking about bets. Because everybody understands that if you make a bet and you do well, it could just be luck. It could just be luck. So that acceptance of uncertainty, understanding there is uncertainty, is unavoidable. So it's right there in front of us, and if we don't hide the betting aspect, we don't have to worry so much about communicating it. You know, communicating the uncertainty because it's in our face. So you see what I'm claiming, that the language of betting can clarify what our statistical studies can and can't do, and clarify the games that scientists actually do play and have to play. So here is the basic idea, and you've heard me say this in other ways, but now I'm presenting it as a way to teach elementary statistics better. The idea is that if you want to test a probability distribution, that's the big topic. That's the first thing that's taught in these elementary stat classes to 1 million students a year in the United States. How do you test a probability distribution? So my idea is, how would you test it? Somebody says, these are the probabilities. You say to them, put your money where your mouth is. I want to bet at those probabilities against you. And I make a bet against you, and I multiply my money by a lot. And that would be so a bet is a non-negative payoff. And when you tell me a probability distribution, and I take a non-negative payoff, the expected value, you should sell me that non-negative payoff, which depends on how things come out, which you have probabilities for. You should give me that, you should sell me that non-negative payoff for its expected value. So I've invested the expected value, I get the payoff back, how much should I multiply my money? If I multiply my money by 1 million betting against your probabilities, there's no better way I could. What else do you want? That's the best way. That's the best thing I can do to refute your probabilities. Because probabilities about betting, everybody knows that. That's the idea. Now, that is elementary. It's obviously an ancient idea. The curious thing is, I cannot find it written down anywhere in anything that I didn't write. And you know, I pose this as a challenge and a question because I don't want to go brag about something that I think people have known about forever. Say, oh, I invented this. I don't think I invented it. But I think everybody knows it and everybody's hiding it. That's why. Everybody knows that's the way to bet against a probability, but they're hiding the fact. So what if we put it on the table? What do we get? So this is the notation I'm using. So you claim that a phenomenon Y is described by a probability distribution capital P. The payoff is a function of Y. When we find out what Y really is, that's the outcome. And I get that much, F of Y, F of little y. I have a little historical sidebar here that having the capital Y for the unknown and the little y for the actual value later was that notation was introduced by Andrei Markov in his book in Russian in 1900. So my point is that this is a large betting score, is the best evidence I can have. But even if I beat you 1,000,000 to 1, we're still realize it's obvious. I might have just been lucky. This is the best evidence I can have against your probability distribution, but I might have just been lucky. We all know that. We have to live with that. In red. This is not a Bayesian story. This is not about utilities. This is not about, because I can risk a penny. It's purely demonstration.
I don't think you have to be, it has to be about utilities of your Bayesian.
Well, anyway, it's not about, I'm risking it, I don't even care about it. It's a demonstration. I don't have to believe that my bet is going to work. I could just be a whim. This is what I'll try. Try this. Try something else next time. I'll try this. And I just risk a penny. Or $1. I don't care. $1. I can risk $1. I don't care about $1. Certainly don't care about pennies. So you can risk any small amount because you could multiply your bet and you could also multiply the expected value. So it's a factor. You multiply what you pay for. The factor by which you multiply the money you put up, the money you risked. That's the betting score. So it's invariant to the amount that you put up. So here are the usual ideas that people in non-Bayesian frequentist statistics, the usual ideas are likelihood ratio. That's the probability that I'm testing P. P is your probability, I'm testing it. I might have an alternative Q. That ratio is called the likelihood ratio. The significance level, if my test is one that the usual idea is not that you're testing by betting. The usual idea is that you have a test that either accepts or rejects. And the probability that it rejects your probability distribution if your probability distribution is true, that probability is called the significance level. We write alpha for that. We also look at the power, which is the probability under the alternative distribution that you might think of, that the test would reject P. And then there's the p-value, which is what everybody uses. You get a test statistic that you think shouldn't be too big if P is true. And you look at the probability that it comes out bigger than what it really is. That's called the p-value, and you want that to be less than 5% or less than 1% or as small as possible. And when it's very small, when it's less than 5% or 1%, you put a star on it, and you say the test is highly significant. We've proven something, and we can get our paper published. That's basically the game that all my PhD students, all the PhD students I ever knew, basically that's the game they're playing to try to get jobs at teaching finance and accounting, or management science, or management or marketing. They're all doing these empirical studies like this, and we have students in psychology doing the same thing, all of these interesting. Power is curious. Power is, the mathematical statisticians say you really should have a test, you should pay attention to the power of the test. The power of the test is as unknown to these practical people as Bayesianism. They ignore this. My students, my graduate students who've taken stat courses and are applying statistics, they've never heard of power. Even, well, they've heard, I think it went in one ear and out the other. You never see it in the articles. It's ignored. So so I'm going to show you the game-theoretic, the betting interpretations of these things. Turns out likelihood ratio is the betting score. I told you what a betting score was, right? Betting score is how much I multiply my money. Well, it turns out that's a likelihood ratio. The significance level is the inverse of a betting score. For a winning bet, it's all or nothing. See, that's the idea. The usual way of testing a hypothesis is you say, okay, I'm going to reject if this happens. A particular event happens. Okay, so if that event only happens 5% under your probabilities, then I can regard that as a bet. I only have to pay 5 cents for a payoff that gives me $1 according to your probabilities. So that's like a test that multiplies my money by 20 if the test rejects, and multiplies it by 0 if it doesn't. So it's an all or nothing bet. I don't have to do all or nothing bets. I can do something more clever. But the significance test is like an all or nothing bet. And a p-value is really cheating. By this, I'll show you that it's cheating. So these are the betting interpretations. Well, first of all, let me explain why is a betting score a likelihood ratio. So what is a bet? I define the notions bet and betting score. I said bet is a payoff that's non-negative and has expected value 1. Now for simplicity, they make this expected value 1 because we're only interested in how much the payoff multiplies. So we can make the expected value 1. We make it non-negative. Why is it going to be non-negative? Because I can't risk more than that $1. And the question is, how much is it going to multiply the money I risk? And if that's going to be negative, that means I'm risking more than I paid. I might have to pay more. So I choose a non-negative F that has expected value 1 with respect to the probabilities I'm trying to beat. Okay, this is in symbols, non-negative, expected value 1 means I multiply the possible outcomes by their probabilities and add up to 1. What does that tell you? That tells you that F times P is also a probability distribution. Because if you took F times P, it would be probabilities and add to 1, and they're non-negative. P is non-negative and F is non-negative. So, F times P is a non-negative probability distribution. I'll call it Q. So my bet defines an alternative. This betting concept, the probability, you may not even know or think that you have an alternative probability distribution. But the bet, if this is the way we play the game, if the way to test is to make a bet of this kind, then there's an implicit alternative, Q. So the betting score actually is a likelihood ratio. The bet defines alternative hypotheses, and actually a payoff is a bet if and only if it's a likelihood ratio. I mean, I've proven it one way, that if you start with a bet, you get the likelihood ratio. But if you start with the likelihood ratio, the same calculation shows that that's a bet. So a bet and a likelihood ratio are the same thing.
So the likelihood ratio captures the evidential import of the experiment.
Bayesians think that. Other people think that. R.A. Fisher, who was an anti-Bayesian, argued for directly interpreting the likelihood ratio. I found other statisticians who have supported, and it actually goes back to the 18th century. Even before Bayes, people had the idea of interpreting the likelihood ratio as measuring the evidence. But the funny thing is, the curious thing is, these R.A. Fisher and the other prominent statisticians and mathematicians who said we should interpret the likelihood ratio as a measure of the evidence, none of them interpreted it as a bet. I cannot find it in writing anywhere that they interpret it as a bet. It's like this is hidden knowledge that it's a bet. Because betting would make statistics sound not serious enough, not objective enough, not scientific enough. So if we don't have to go Bayes, we don't have to go all the way to Bayes, just interpret the likelihood ratio as a bet. That's the core idea. Now, we have to think a little more about that. I'm going to bring up. So, I proved to you a likelihood ratio is a bet, and vice versa. But, and if you just start with a bet, it produces a likelihood, it produces this alternative Q. But what if you started with Q? What if you started with alternative Q? Well, that is sort of I did. You're the one, you have the probability P, but I'm going to test and make a lot of money. But what if I had a Q? What if I said, I don't think P is right. The way I'm going to bet is I'm going to think about what Q would tell me to do. Now, should I make my bet P over Q? Or rather Q over P? If I start with the idea that Q is right, your P is wrong, my Q is right, if I start with that idea, I haven't told you anything yet to convince you that I should make Q over P my bet. There are other things I could do. If you think about what choosing Q over P actually does, is it maximizes the logarithm of the bet. It maximizes the expected value under Q of the logarithm of the bet, of the outcome. So if I choose to make the bet Q, if I choose to make Q over P my bet, it looks like I'm trying to maximize this quantity. I could maximize something else. I could instead maximize Q, the probability under Q that my bet comes out bigger than 20. If this is what I want to maximize, I would do a Neyman-Pearson 5% test. That's what Neyman and Pearson proved. Famous Neyman and Pearson lemma. They proved, they told what test you should use if you want to maximize this. But instead, I'm not just doing a 0 all or nothing test. I'm going to do Q over P. That means I'm trying to maximize this. Now, why would I want to do that? Why would I want to do that? And the answer is, the reason I would want to do that is because this test I'm doing science. I'm not doing acceptance sampling. There was a big argument about this between R.A. Fisher, not about my way of betting, But there was a big argument between R.A. Fisher and Neyman. Because Neyman was explaining that you should maximize this. And Fisher said, that works okay for acceptance sampling for a manufacturing plant that's deciding whether to throw out or keep something going off the assembly line. But that's not for science. In science, you're not doing decisions here. You're trying to find what the evidence is. So I agree with Fisher, but I'm going a step further, and I'm saying, what is the game the scientists are playing? Fisher basically said the scientists aren't playing a game. And this point of view says, okay, the scientists are playing a game, but the scientist game, this is a better goal for the scientists than this is. And why is that? That is because this is not the only test that we're going to do, or that the science in general is going to do. If it was, if it's just if this is just a assembly line, and we're testing whether this, thing going on the assembly line is acceptable or not. If it's not, we throw it out. If it doesn't pass the test, we throw it out, and it gets reworked and made into another Git widget. Okay, that's it. There's not going to be another test of that thing. Fisher said that's what neyman-pearson is for. But the science, this test is going to be one step. Somebody else should come along and test it again if they want to have confidence, or we want to keep learning. Or we might not want to be testing it, we may be testing related things. So this needs to be part of a story that captures something about science. And the reason it is because the reason you want to maximize the logarithm of a payoff is because what you might be trying to minimize is the product of many successive many factors. So the idea is if we do one test after another, if I do a test and then somebody else does a test, somebody else does a test, we would rather multiply the payoffs together than average them. That's the idea. And there's a lot of areas outside of statistics. I listed some. Gambling theory, information theory, finance theory, and machine learning. I give references in my paper. All right, all those fields, people have maximized the logarithm of the payoff because they wanted to maximize the rate of growth when there are many steps. That's what maximizing the logarithm does. You can see, well, obviously that would happen. You can see how that's, how in finance and gambling, that's the obvious thing to do, but it's also true in information theory and machine learning. This thing is called, this expected value of the logarithm payoff is called the Kullback-Leibler divergence. So it's not something brand new. So here is why, here is my story about why in the scientific enterprise this is what you want to do. So say that this probability distribution doesn't just describe a one-shot phenomenon, but it describes Y1, Y2, and so on. So I test it using Y1, and I get a betting score based on Y1. And let's say it's mediocre. I didn't multiply my money by 1 million. Maybe I multiplied my money by 1.5. Big deal. The fact that I multiplied my money by 1.5 is not going to wow anybody. So let's say somebody else tests, or I do. I just keep testing. I say, well, let's get some more observations. Let's test it some more. So I do another test. And let's say it comes out mediocre too. This time I multiply my money by 2. So, you know, the point is, there's two ways you can think about what's going on. One way is that the second test, I can take another $1 out of my wallet. And then what's happened? I've risked $2. And I got the 2 payoffs. But I risked $2, so I got it divided by 2. And if each of these is mediocre, their average is mediocre. I'm not accomplishing anything. On the other hand, if I did the first test, if I took the winnings from the first test and invested those in the second test, I'm just keeping betting. I've got this money. I still just risked the $1 I started with. So then the betting score is F1 times F2. And this is obviously a better thing to do if our test is not a one-off accepted sampling in the science enterprise. So that's why we want to for a large effort. So that's this.
And just so I follow this, Bayesian would say the same thing that you're saying, but when you do talk about it in terms of N, you talk about it in terms of posterior probability. But it would be the same thing. Bayesian would also think that.
Well, they would multiply the odds, but they wouldn't give my reason for it.
What?
They would multiply together the likelihood ratios, but they wouldn't give my reason.
It would be of your reason.
And their reason.
Their reason.
And their conclusion would not be mine. If I multiply these together, the product, I might even put in a prior. But what would my prior be? I would say, well, I think I have some prior evidence, and that's like multiplying my money by 2. So I can put in a prior. But in the end, what do I have? I have a number that says how much I multiplied my money by. If I multiply my money by 1,000,000, I'm not telling you that I would bet on this thing 1,000,000 to 1. No, I'm telling you that was the outcome 1,000,000 to 1. That's totally something different than saying I would make a new bet on Q at 1,000,000 to 1. Nobody would say, no, that doesn't justify that at all. So the conclusion, so you can make it look formally like Bayes, but the logic is not Bayesian, and the conclusion is very far from being Bayesian. The conclusion is just, this is how much we multiplied our money by. And the uncertainty remains glaringly in view that maybe these scientists were just lucky. This might weaken science. I don't know, the climate change deniers who might have a problem. They say, oh, you don't know, this might weaken this kind of candor about our remaining uncertainty might weaken science, but I think they would also have some gains about the honesty. Yeah.
This actually relates to last time when you talked about this. You said something, you should correct me if I got that wrong, which is that when you do this multiplication of the 2 mediocre returns, it does not rely on independence assumptions between...
Well, of course not. Because, I mean, you don't need to rely on independence because you could be... if your probability distribution P claims dependence, then I'm using your probabilities for Y2 given Y1.
Yes, so that was my question, because if I betted against you for once, and I realize that my bet is, I can learn from the fact that whether I have won or lost against you, and then revise whether I should bet on the second one again.
You can try it. That's right. What happened the first time can influence what your Q2 is.
Right, and then in order for you to be able to multiply them.
There doesn't have to be any. P is the denominator is going to be P of Y1 and P of Y2 given Y1 because you've got a comprehensive probability distribution. But I've got a Q1 up here and I've got a Q2 up here. And I can do whatever I want. The logic is I'm going to fool around and try to find a way to make a lot of money off of you. I could start with a comprehensive Q and condition it and also do Q of Y1, Y2 given Y1. But I don't have to do that. And moreover, it might be somebody else doing this one. I did this one.
Are you the one that's endorsing Q or P? You are the
tester.
The tester.
The way I'm talking, you are P.
Yes.
You are P, and I'm challenging P. So I started by saying P gives probabilities for the whole thing. It's comprehensive.
But you must revise your Q2 in accordance to what you observe at Q1, right? Because otherwise
what I'm saying is, I might be testing, the first test might be what I did. Now I go home. This is a scientific enterprise. Eddie comes and does a second test. And he's going to look at, you're now saying these are the probabilities for Y2. Eddie says, okay, I will use a Q2 against that. Eddie is not going to condition my probabilities. He's not me. He doesn't know what I might have thought about Y2 before. He has to come up with something new himself. So there's no reason why the tester has to be acting Bayesian. And in general, it would be impossible for the tester to act Bayesian because the tester is an entire scientific community.
You have to be having the same tester to do this.
No.
Otherwise, how do you argue for the compounding of the...
The compounding is just this. I made this much money. We made this much money. We're making money off of P. We made this much money. We multiplied our money by 5. So we started with $1, now we got $5. Now we multiply it by this, because we don't just invest $1 in the new bet, we invest $5. So if this is 2, if the betting factor was 5 here and 2 here, then the scientific community has turned $1 into 10.
I'm also puzzled by this. Suppose there were 2 people, you were betting against 2 people, and you make, they make...
No, I'm betting against a theory. Against probabilities.
Right, yes, but there's somebody, I see. So in other words, the maximum amount you can get is what you get in this bet. I was imagining, in order to enforce the idea that you really need an independence assumption, is that that there'd be 2 other people who supported the alternative hypothesis.
No, I can have the second tester can have a completely different idea.
Right, he can be, but I was imagining, thinking, what if he had exactly the same idea as the first one did?
Well, the Y2 is also different.
And used these, and saw the same, made the same observation that the first one made, and then
that's
there would
possible. You could do that, I mean, but that's not necessary.
No, it's not a question of being necessary, it's a question of whether you want to add the winnings together to say what the...
You don't are adding the winnings, you're
multiplying the winnings.
I'm taking the winnings from... So we think of these winnings came to the scientific community. So it's all hypothetical. It's, but the point is that if the scientific community finds a way of betting against P and multiplies their money by 1 million, that's the best evidence we can have. And it doesn't matter that the way we... And so the point is that this gives us a theory of meta-analysis. And that's what the problem is, that our current testing theory doesn't allow us to go beyond that single test. It's like it's acceptance set. And this is saying we can fit it into a scientific enterprise. And so this is one way that works. We do one test. We have a probability distribution, and we do a test, and then somebody else comes up with a test. If we multiply by saying the second tester is going to take the winnings from the first and multiply it, then we have a way of putting the evidence together, which we currently don't have in the theory of analysis. Another example is the one that Jacob Feldman, who attended this seminar a while back. Jacob was talking about that he's got a psychology lab. He's interested in some phenomenon. Somebody had a theory that people react in a certain way to something. He says, well, let's see if this little bit different thing works. So he has a kind of general idea of the thing he's looking for. He tries one experiment, gets a bunch of students to subjects to see if something makes a difference, tests whether it makes a difference. Not enough to publish. So then he changes his idea a little bit, does another experiment, sees if that's significant enough to publish. He does that 20 times, and he finds one that's significant than 5%. Nobody publishes it. Okay, so people have recently recognized that half of the studies published in the leading psychology journals are wrong because they're generated in this way. Now, one way of doing that would be to say, okay, Jacob, you've got to put up $1 every time you try something new. And so when you find something that looks significant, it's not enough to multiply $1 into 20. You put up $20. So you've only multiplied 20 by 20. That's too hard, Jacob said, we can't do that. That's too hard. But if we think about it, okay, if we think about it in betting terms, that first experiment didn't lose all its money. It wasn't good enough to publish, but maybe it's multiplied its money by 1.1. Or maybe it's multiplied its money by 80%. Maybe he still has 80% of the money. Okay, so take the money from the first experiment, try to multiply it. then try to multiply that in the next experiment, so that you are testing the kind of big idea that you're trying different versions of. And you could write a report and say, this is what I did. And at least this gives an opportunity to be honest about what the laboratory is doing by giving a betting interpretation of the larger enterprise that you're in, instead of just trying to put a p-value on each of the studies. That's the idea. So that is the, this is a bunch of articles about likelihood that don't mention betting. Fisher's book, my old friend Tony Edwards, he's in his 80s, but he's still around. He wrote a whole book about this, but he doesn't mention betting. Art Dempster, my mentor in '73, he wrote a big article about directly interpreting likelihoods. That article had discussants, very prominent statisticians. David Cox was one of the discussants, George Barnard, big British names. And then it was republished in a journal in 1997. And more big names discussed it. Nobody mentions a betting interpretation. So it's sort of like, this is being missed. Okay. So here's adding an idea to what I've been preaching. This is what I call the implied target. So the idea was that if you have an alternative, what I tried to convince you was, if I have an alternative Q, then what I want to do is maximize the logarithm of my betting score, of my payoff. Now you can rewrite that. The expected value, you multiply the probabilities times the logarithm, add it up. But of course, Q is equal to P times F. Q is equal to P times F. So this is now the probability with respect to P, expected value with P, of F times logarithm of F. So we can write the target, what you're trying to maximize, as a hiding Q. This sort of makes it, the point of doing this is it brings out as soon as I tell you F, I'm not only implied a alternative probability distribution, but also implied what I am trying to accomplish. I am trying to accomplish a logarithm of F of, this is the expected value. I'm trying to get something in this ballpark. Now, there's a logarithm there, so if I wanted to know what is it I'm really trying to, what is my goal here? But how much with this test and this sample size? Because, Q could have, this could be, Y could have components x1 up to xn, and P could have components x1. So this ratio, this sample size is in there. So it's how powerful this test is, it needs to be measured somehow. And usually it's measured by the notion of power, but the notion of power applies to these 0, 1, all or nothing tests. So I need a notion, something like power for my test. And what that would be the exponent of this. E to the thing I'm trying to maximize. This is the amount, roughly speaking, I have to undo the logarithm. So this is kind of the betting score I'm aiming for. I'll call this my implied target, the betting score I'm aiming for. So I could write it like this, or I could write it like this. And I thought it was fun to write it like this. I actually just sent this paper to my colleague Volodya. He says, "Why are you hiding Q?" I said, well, we might not, the person doing the test might not notice Q. He might just come up with an F. He might not say, I'm trying to do a Q, but I'm going to say there's still an implied target. And we can write either like this or this. It's the same thing. So I'm saying you should tell what the implied target is. Now, what if the implied target is not very high? What if the implied target is 1.2? There's no point in the test. This test, the best, this means that if this test gave you something significant, if this test multiplied your capital by 10, it can only be because you're lucky. because the test is only trying to multiply its capital by 1.2. So this is a case where you know in advance that if you get to something significant out of this, it's by chance, or probably by chance. It's not going to be credible. So you shouldn't do the test. So the implied target, it would be something to evaluate whether the test is worthwhile. Usually people talk about power, but nobody buys power. Power is too hard. So my idea is that this would be easier to communicate than power. For one thing, people don't want to tell what the alternative is they're testing. Because if their sample size is not very large, they want to say, well, I can't say how much of an effect I need to be interested. They kind of refuse to tell what the alternative is reasonable. And maybe you don't know what alternative is reasonable. But as soon as you say what the test is, you imply one. So you're kind of in a position to enforce, that is, the journal editor is in a position to enforce some consideration of power, which we're not in a position to do now.
I just had a comment. I thought it was very interesting because you pointed out earlier. So the EQ of log of f, that's the KL divergence between Q and F, Q and P.
Yeah.
So an e to the power of that is a monotone function of that, which you supposedly should maximize if you're trying to increase power, which is in this in your analogy. Just the max n type of updating, where people try to find a Q such that the KL divergence is minimal compared to the P as a desirable property, because you are not supposed to inject more information than you have. That is basically working exactly against this goal of maximizing power.
So here is the way I would report a statistical test. First, we have a proposed study, and then we have the results. The proposed study, you'd say, what is the phenomenon? What is the probability distribution that I'm testing? What is the bet I'm going to make? What is the implied alternative? And what is the implied target? And I don't have a symbol for that. Maybe I should make up a symbol. I couldn't think of a symbol. T is usually used for tests, so I'm going to what would be for a target. And then, if the implied target is not good enough, you shouldn't do the study. It should not be publishable if you don't have a good implied target. It's like a test without power. But then you see what the actual outcome is, and you see what the betting score is. So my proposal here is, if it has a good implied target, you've learned something even if the betting score isn't good. You've learned that you're really favoring the null hypothesis, the P. So maybe we could decide whether to publish things based on what we see before the study, not just the outcome of the study. That would be an idea.
There's people doing that.
Pardon?
The people are trying to do that.
Are trying to do that with the concept of power.
I don't know. Are they? Is it based on power?
What else would it be based on? We don't have this idea.
It's a bit ambiguous. It's based on the methods used. So it's instead of basically letting people look at the results and decide to publish, you're submitting your methods, designing your study, whatever, to the journal.
It's going to be power they're talking about.
And well, I'm sure it varies from place to place, but I think they're trying to be a bit more open-minded in that they don't want to say you have to maximize this criteria like the p-value, or optimize this criteria, because they're saying that's what's the problem in the first place. So I don't think that they have like a strict number, quantity in mind, but it's more about the method. And if they say that, well, this study looks like it's worth doing, then we'll publish whatever you get if it's significant or not. I mean, that's what certain people are behind right now. But it's not what you're suggesting. But yeah.
Well, this would be a version of that.
It would fit. I think it would fit into that idea.
Yeah. This would be a way of implementing that kind of idea.
For the sake of somebody who's drunk patient, that's me.
Yeah.
With the list, how would you think of the list here? Bayesian would agree, well, it's initially an unknown outcome. There are two hypotheses, or however many hypotheses. somewhere. No bet. No implied alternative. The alternative is explicit. And an experiment. And the experiment, one can say beforehand what the possible outcomes are and how likely results are, what the posterior probabilities would be for that particular experiment.
I don't know that.
I'm just trying to see what's the.
Why is it?
It might be that you think that it would be crazy to have people who are educational psychologists or medical testers being Bayesians, because they would have to include prior probabilities into them, and we don't know where they would come from. I'm not sure what you're worried about the Bayesian approach is.
Well, it's not my worry so much as that the communities by and large don't buy it.
But you want to convert them too, right?
Yeah, but they haven't considered this idea. But the problem there is this doesn't tell what my prior opinions are.
Right.
It just says this is the way I'm going to bet. It doesn't put in my subjective opinions. It says I'm going to do a test, and this is the way I'm going to do the test. That test might be motivated by some prior opinions, but all I'm telling you is I'm going to do the test. Whereas the Bayesian story has to have these prior opinions, and the journal editors don't want to hear about it.
Right, so that could be an advantage to Bayesian, because they're explicit about what their prior opinions about.
What I said is the journal editors don't want to hear about it.
But you want to change them, as the journal editors.
Well, the Bayesian's been trying this for a while.
So maybe strategic-wise, your suggestion is a better change. But theoretical-wise, I want to understand, I want to see whether this really is an alternative to how to think about scientific inference. And I don't think I understand it well enough, partly, but to the extent I understand it, I don't see that it's an alternative to the way Bayesian would think about scientific inference.
Well, this is not all of inference, this is testing. I don't even, probably I won't have to talk about too much more than testing. But, if we want to talk about scientific inference, we also need to talk about statistical estimation. So I haven't gotten there. But this is just about testing. It's about something that comes close enough to what 1 million people are doing that maybe it could have some payoff. But it also obviously has my philosophy of game-theoretic probability underlying it. So I've already basically told you about significance levels, that power is usually ignored. So here is an example, a kind of a motivating example. And Gelman, this example comes out of that paper by Gelman and Carlin. And Gelman says, and I think he's right, that this example is at the heart of the replication crisis. P says that the phenomenon is normally distributed with mean 0 and standard deviation 10. Q, the alternative, says it is normally distributed with mean 1 and standard deviation 10. Now, in this case, in Gelman's story, what does he mean that Q is the alternative? The question is whether something has an effect. The null hypothesis is the effect is 0. The standard deviation of 10 tells us about how hard it is to measure the effect. And Gelman's assertion is that 1 is the biggest effect you could possibly have. So you're not necessarily a Bayesian. You don't have exact probabilities for what the effect is. But you know it can't be any bigger than 1. It's just not plausible. It's not reasonable. But the effect for, because of our general understanding of the situation, the effect can't be bigger than 1. So if there's the most extreme alternative that we could consider would say that it's got mean 1. Okay, but we do the measurement, it comes out 30. That's highly significant. Something that is standard deviation 10 comes out equal to 30, it can't possibly be 0. So you put any reasonable significance level, you're going to reject the null hypothesis.
Sounds like
so-
maybe you should reject the other hypothesis too, and
Well-
how you started it, what your prejudices were when you started.
That's exactly the problem. But the problem is that because you don't state the other hypothesis, you just state the p-value, you get the paper published. So this is basically the problem with, not to exaggerate, but half of the articles in the leading psychology journals. This is half is an exaggeration, but this is the fundamental problem. And I'm quoting Gelman as saying that, and I think it's essentially why it's the biggest issue. What was happening? Okay, so we can nod our heads and say, oh, they're so stupid. But it's the whole damned. It's not just psychology. It's the whole. All the professors in the business school. That's what they're doing, and it's happening in medicine too. And we've had serious, misunderstandings and mistakes in medicine because of this kind of mistake. And people don't want to. They don't want to say what the alternative is. They've got a study that it's not big enough, there's not enough observations, it's not powerful enough, but they don't want to say what the alternative is because they don't really know, I'm saying that one is the biggest it could be, but we don't know. Let's try the experiment. My sister has a PhD in psychology. First she did a master's degree. When she did a master's degree, she asked me whether her sample size was big enough. When she did a PhD, she didn't ask me. Because she didn't like the answer I gave her. So the mathematical statisticians may understand this, but you have a lot of sociological factors that are keeping, the mathematical statisticians' understanding from penetrating, because people want to get PhDs, they want to get master's degrees, they want to get papers published, and so on. So what happens if the statistician A uses the neyman-pearson test in this situation? Even if his significance level is this small, you'll still reject when y is bigger than 30, so he rejects. What is the likelihood ratio? The likelihood ratio is this, and it comes out, he put a 1.34. So the statistician A, who uses a neyman-pearson all or nothing test, multiplies his money by 666. The likelihood ratio guy, the guy that does Q by the likelihood ratio, he multiplies his money by 1.34. This is obviously not an impressive result. But the prior the implied target, this is wrong. Here I have the implied target is less than 1. That's not possible. I corrected these slides elsewhere. This is a mistake I had on the slide when I gave you the stat department. It's not less than 1, it's 1.2 or something. But anyway, even the implied target, still need to correct that slide. Even the implied target is only a little bit bigger than 1. So this is a test that should not have been done. You could also say it's not been done because the power is small. The power of the neyman-pearson test is only about 6%. Should be 90 something, right? But it's only 6%. So Gelman using power, the standard mathematical statistician is using power calculations, would have said this test wouldn't be done, and the implied target tells us the same thing. This test should not have been done. Wasn't worthwhile, even though it rejected and got the paper published. So here's another example, and this is an example that Debster made up to show that even a test with good power may give a misleading result. So in this case, this is an artificial example. You can object to it and say nobody would ever use this example. But it just illustrates possibilities. So here is where y is between 0 and 1. And p is uniform on 0 and 1. That's p. That's p. But q looks like this.
This is Q. I'm sorry, I put it the other way. Q looks like this. Q concentrates the probability very close to 1, extremely close to 1. So a 5% test would reject when y is bigger than 0.95 because the Q probability, 95% of it is below 0.95. So there's only a 5% chance of being up here, so it would reject if it's, so that's a 5% rejection. That test, and under Q, you're very likely to be up here. So that test has power 99.8%. So this is an example that you give a test that's very powerful and has a low significance level. But suppose you got a result that was just barely significant. Suppose you observe 0.95. What is the likelihood ratio? The likelihood ratio is 1/4. So even at the 0.9, the point is that this thing is so peaked here that even at I'm going to draw it right. It's so peaked that even at 0.95, you're only at 1/4. So if you observe the value 0.95, the likelihood ratio is telling you that this observation is more likely under the null hypothesis. Q only gives 1/4 as much probability to it as P does. So you've rejected with an extremely powerful test, as high a power as anybody could ever ask for. But likelihood ratio test, and this betting test that I'm recommending is saying this test, this is, and also you have very low, this test also has very low, it is very high power, but it has very low implied target. So it's an extreme example showing that if the likelihood ratio is what you're really looking at as your evidence, you should have known before you did it that this was not a good test, even though it had 99.8% power. So this is kind of a this is a point for a talk with an audience of statisticians to convince them that my concept of implied alternative is better than the concept of power.
So intuitively, when response to this, you would say, well, you really haven't thought of there are better alternatives that you could have thought of here, which would make the likelihood of getting this result much higher on the alternative.
You can always say that.
What?
You can always say that.
No, right, but I mean, in this particular example, one would question these two alternatives. But if you were absolutely sure that these were the two alternatives, I don't really understand exactly why you're saying that. What's the likelihood of getting this result on the P hypothesis?
The P hypothesis is likely to get something much bigger than 0.95. But I wanted a 5% test.
The Q hypothesis.
Under the Q hypothesis, it's much more likely it's likely you would get something much bigger than 0.95. That's why the power is here.
Right, but to get exactly the value 0.95 would be very, very unlikely.
To get exactly 0.95 is 0 under those values.
Right. If you get a little bit of region around 0.95.
Then you've got the right ratio. It's 4 times as likely.
A little region around 0.95.
Yeah, that's what the likelihood ratio means. It means in a little ratio, in a little region around 0.95.
A little region, okay, so a little region around 0.95 is more likely that you get that result under P than under Q.
4 times. That's what the likelihood ratio is. You just put a dx in or a dy.
Yeah, so it is puzzling what to say then. So
well, it's saying that this concept of power is not on target. This example was made up by Dempster, who was not giving my betting interpretation.
But
He was just arguing the likelihood ratio is better.
This also seems to push trouble for somebody who's a diagonal evasion.
I don't know if the likelihood ratio is 1.5, then that's this one. It's multiplying.
It makes you nervous. But maybe it's the way of thinking about the region around.
No, I don't think so. I think Bayesian would be very comfortable using. I mean, as you say, it's artificial because we've singled out these two hypotheses, but it's just an example of what can happen. It's really an example against power. Harry?
Yeah, hold on. Now I'm trying to wrap my head around this. So this is saying that actually. Yeah, okay. So if you ran this test and you observed 0.95 under the traditional way of doing things, you would say that you would favor Q.
Reject P.
Yeah. And you're saying under likelihood ratio, you would seem to be favoring P. And are you arguing that this is a point in favor of the likelihood ratio, a point against the other thing, or what? This would seem to be a point against the likelihood ratio.
If you really believe in power.
No, not believing in power or anything.
I mean, Dempster gave it as an example where it's obvious the likelihood ratio is more sensible. That's, in his 1973 paper, that's what he thought he was telling you.
Actually, I don't know if this is even comparing apples to apples here, because in the first case, you've specified 0.95 ahead of time.
Oh, no, here you did. I'm sorry, oh, no, here you specified a 5% test. So 0.95 happens to be a place where it's just barely significant.
That's it. But in the when you do a likelihood ratio, you don't specify anything, right? You're just going to observe something and calculate the ratio.
Yeah, that's right.
So the 0.95 has a bit of a different significance, I would think, in those two situations.
You know, I did make, I don't know if this is helpful or not, but I did make this comment at the top, that the likelihood ratio is always more conservative than the Neyman-Pearson test.
Okay.
That's Markov inequality. But this is a case where it's extremely more conservative. That if you set this as your significance, if you set ignore this first paragraph. In example 2, statistician A's implied target is 20. B's implied target is 10 to the 53. It's ridiculous. And it came out, not only did it not come close to its implied target, but it actually favors the other hypothesis by likelihood ratio. So from the betting point of view, this outcome really seems to favor P. So, okay, so that's just an example. So what is my point? That we can communicate statistical results better if we use the language of betting than if we use this conventional idea of the way people test. Now, maybe I'll say a little bit about point 2, but let me get a little more philosophical. What is the conventional method of testing? The conventional method of testing is that we test probability distributions by looking for events that have small probability and seeing if they happen. That's Cournot's principle. We reject, so this, most of you have heard me talk, you've all heard me carry on about Cournot's principle. So statisticians, whether they say it or not, you could infer that their philosophy of probability is Cournot's principle. That's, you know, if the meaning of probability is how you test it, okay, that's an if, but if in practice, that's the practical meaning, it's how you test it. They test it by looking, singling out events of high probability, and if they happen, you reject. So this betting thing is kind of like Cournot's principle, but it's not exactly the same thing. It's you single out ways of betting against the probabilities, and if you multiply your capital by a large factor, then you reject it. So this, in this philosophy, the meaning of probability is betting offers, basically. So that is a So the point is that the meaning of probability is not frequency. We have an objective meaning of probability. It's objective. It's objective in the sense that we're asking whether the probabilities describe a phenomenon. Now, there's a subjective part because we're testing. And we're allowed to test it any way we want. And in practical problems where we actually see the observations, it's the way we try to make that objective is they say, well, you've got to say what the test is before you see the outcome. If you see the outcome, then it's not. Of course, something with small probability happened, but you've got to, you can't wait and see what it is. You've got to say in advance what it is you're going to reject. And so the betting interpretation is like that. Now, I think I may have said this to you before, but I'll repeat it. There is, if we have a lot of data, if there's something that where there's a lot of data, then the difference between these kind of bets that can have different, the Neyman-Pearson testing, the all or nothing testing, there's only two outcomes to your bet. You lose all your money or you get a certain amount. But I'm talking the likelihood ratio is bets that can come out at many different levels. And that kind of gives you measures the strength against the evidence and allows you to combine that evidence with other measures of testing, other tests also. That's the meta-analysis part that I'm telling you, part of being part of the scientific enterprise. If you have an immense amount of data, then the difference between the two approaches kind of becomes not so important. It's true that the likelihood ratio is more conservative, but if you have enough data, that doesn't matter. You're going to reject if it's wrong. Now, but also, if you have enough data, it doesn't become quite so important that you select the test in advance. Because you could say instead that you want the phenomena, you want the probability distribution to pass simple tests. And there's only a limited number of simple tests. And you have enough data, you could say, well, it's got to pass this 1,000 simple tests. And I could put a penny on each of the 1,000 simple tests. And if one of those tests multiplies my capital by 100 million, I've multiplied my capital by, it doesn't matter that I lose 999 pennies, that one penny I had will give me a betting factor of, orders of magnitude. That's a philosophical comment. So, so the next thing I was going to talk about was that by defining fully defined betting games, we can also interpret statistical estimation in terms of betting. All I've done, so traditionally the statisticians think two things are going on. One is that you can test a probability distribution, or you can estimate what probability distribution fits the data best. And that was, so let me remind you. So the usual formulation goes back to Fisher in 1922. The vocabulary for talking about this is that a statistical model is a parametric class of probability distributions. So the setup is that you know that the probability distribution that describes a phenomenon is one of these, but you don't know which one. So you want to estimate theta. And Fisher did not like the idea of doing so. The Bayesian knows how to estimate theta, but he has to have prior probabilities for theta. Fisher wanted to estimate theta with a maximum likelihood estimate and talk about procedures for estimating theta, but he didn't talk about, and sometimes he talked about, in his 1956 book, long after he first talked about this, He said, well, look at the likelihood function and look at what the maximum likelihood estimate is and cut off at 1/15 of that maximum likelihood estimate and say, look at the interval of values of theta that are at least 1/15 as big as the maximum one. And figure those are good. That's a good, probably theta is one of those. That's the way he said, that was one of his ideas for directly interpreting likelihood. You don't put any prior probabilities, you just look at the values of theta that have high likelihood and say, oh, it's one of these. That's it. So, how does this betting approach go? So, the point is that we have to define a game. I could talk about this testing. I said, you know, you have the probability distribution, I'm going to bet against it. I wasn't very specific about a game with players and how the rules of play and who wins the game. But if we want to do statistical estimation, we've got to start doing like what we have in my book with Bologna. We have to specify the game. And what is interesting, and the Fisher's partial knowledge, this is kind of the key idea, which it would take me another hour to exposit, or 2 hours or something. The key, and it's in chapter 10 of our book, the key idea is that the way the knowledge is partial is the statistician does not see all the moves in the game. The statistician only sees some moves in the game. I have probably already showed you so let me talk about a couple games. Put that on the table a minute, then I'm going to talk about games where the statistician doesn't see all the moves. Let's first of all think about a game where everybody sees all the moves. Certainly the players see all the moves. The games we're going to consider, the players all see all the moves. So here we have the player who makes the bets and the player who decides the outcomes. And this is coin tossing. So there's a game where we have heads and tails, probably 1/2 each. And this is just to set up some algebra, some symbols to show. I've done this in the seminar before. How many of you are familiar with that? Can I take it for granted you understand this? Eddie, have you seen this video before? So this shows how your capital changes when you, and M is a bet that there be a 1. If M is positive, you're betting on a 1. If M is negative, you're betting on 0. Yn is either 1 or 0, so you're either getting a 1/2 or a -1/2 here, and it's being multiplied by the number you choose. So you're betting on a 1 or a 0, and you're betting as much as you want. That's what this says. You start with capital 1. That's like buying a payoff for $1. So if you want to do a test, if skeptic is trying to test this probability of 1/2, he needs to keep all his he needs to keep his capital positive, not negative, because he wants to only risk the 1 he started with. And then we can make various goals for skeptic. Here's one goal. We can say skeptic either wants to multiply his money by 20 or have reality keep his average outcome, and this is the frequency of 1s. Keep the frequency of 1s within 0.1 of 1/2. And skeptic has a strategy that can do this. So if skeptic plays that strategy, it's like buying a payoff. That's making a bet. If skeptic plays this winning strategy, he's making a bet, and he multiplies his money by 20 if the frequency is not close to 1/2. So the point here is that frequency is one of the things one of the ways this probability distribution P has implications for frequency. But we aren't starting with the idea that the probability is a frequency. We're starting with the idea that P represents the phenomena by giving a small probability to various events, and one of them is that the frequency is close to 1/2. So the fundamental meaning of probability is not the probability is equal to frequency. That's not the fundamental meaning. The fundamental meaning is that skeptic will not be able to multiply his capital by a large factor. This won't happen, so this will happen. Skeptic can make a bet so that either this happens or this happens. This one is not going to happen. That's the meaning we give to the protocol. So I'm trying to talk too fast and say too many different things. But my point is that you can have an idea that a probability distribution represents a phenomenon. When you translate that into betting terms, what you're saying is that it's the protocol that represents the phenomenon. And so we say this protocol represents a phenomenon if the player skeptic cannot make a lot of money in that protocol, cannot multiply his capital by a large factor.
Is it that the skeptic will not make a lot of money, or typically will not make a lot of money?
So that's what I mean by saying that the betting, the fact that it might just be lucky, if he does make a lot of money, that refutes the protocol. That's the nature of probability theory, that it keeps in view that anything you say has some remaining uncertainty. And that's the point that Gilman wants us, says we need to reform our teaching of probability and statistics so people will keep this residual uncertainty in view.
I see.
And that's so that we can, so now the idea here is that residual uncertainty is in view. That's the nature of other people say that in different ways. Now, of course, so this is a case where everything is in view. But as I say, betting offers, there are two ways. So what I mean, this testing is really probability theory. When you get into statistics, there's two things that are going on. Partly the game is partly hidden from the statistician. And the other thing is that the betting offers may not be a whole probability distribution. That's the beauty. Robin, who just left to teach, is very interested in imprecise probabilities, where you don't have a complete betting, you don't have a complete probability distribution, you just have some betting offers. Obviously, this interpretation is just as good for that model as it is for a model with complete probabilities. It's the betting offers, the interpretation. If you have a protocol where there's certain betting offers, the interpretation is that the skeptic, the bettor in the game, is not going to multiply their money by a large factor. The other point is that the game, part of the game can be hidden. I want to give an example of a game that's hidden. So here is a game where something is hidden. Let's say the game is that reality announces a vector of regression coefficients. And then reality announces the independent variable. So this is a least squares problem. Y is equal to beta 1 times x1 up to beta p times xp plus an error. So that's what this equation says, except it's indexed with n because you do it 100 times. So reality first announces the regression coefficients, then announces the independent variables, then skeptic makes a bet, and then reality announces the error, and skeptic's bet is a bet on the error. This just says that skeptic can bet the error will either be 1 or a -1 or something in between. It's anything in between. It's bounded error between -1 and 1. Skeptic can bet on that. He can bet a positive amount and get some positive amount times the error, or he can make a negative bet and get a negative number times the error. Any bet he wants to make. So you can, this model, you can prove in this model that the least squares estimate will be close to beta, unless skeptic multiplies his money by a large factor. Skeptic has a strategy that will multiply its money by a large factor unless the least squares estimate is a good estimate. So this is a game-theoretic version of least squares, kind of the standard statistician's tool. But what's going on? The statistician is not in the game. The statistician is not skeptic. The statistician is the statistician hypothesizes that the world is described by a game like this. The statistician is not skeptic. Skeptic sees all the moves in the game. skeptic sees at the outset what the regression coefficients we're trying to estimate are. But what does the statistician see? The statistician only sees the x's and the y's. He doesn't see the true regression coefficients, and he doesn't see the errors. He doesn't know what the errors are. All he sees is what the statistician sees, the x's and y's. And he's estimating the regression coefficient from the x's and y's. So this this game-theoretic story accounts for least squares on the basis that the protocol is the model. The protocol is this model along with the statement, presumption, that skeptic will not multiply his capital by a large factor with any simple strategy. Of course, the kinds of things that the physicists are interested in, something like statistical mechanics, the game is even more hidden. You don't even see x's and y's. You just see macroscopic results. But it could be given the same, the probabilities in it could be given the same betting interpretation. That there's a betting game going on there. That is the way the phenomenon is described by a betting game. So I have plenty of time for discussion.
Oh, you're done now? Or are you going to continue? I just had a question, but...
Well, I sort of said what I wanted to say.
Okay.
I'll let you talk.
I just wanted you to kind of repeat the thing you said, which was about beta having to be the least squares estimate in order for... Or else skeptic can multiply his money by...
I don't think I have a slide for it, but...
Well, I just wanted you to say it. I just wanted
the least squares estimate will be close to beta. Beta is the true regression coefficient.
the least squared estimate at what
beta.
point in time? At each point? I mean, so, you know,
in this case, for simplicity, I assumed 100 observations.
So after 100 observations.
I can give bounds for how close it has to be.
Oh, I see. Oh, okay.
In our book, we prove consistency. If it goes on forever, it'll converge.
Right, okay.
So it's sort of, point is, the way we look at, there's nothing, this is kind of standard statistical theory from the, just kind of showing what kind of interpretation we put in the game-theoretic treatment of standard statistical theory. There's essentially no new statistical theory here. It's how to interpret it. Well, there's other things I can say.
Just clarify on the, so on this idea of interpretation of probabilities, I guess there's a sequential notion of reality analysis, something X and Y's, and then skeptic analysis, reality analysis, skeptic analysis, and so on. Do they have to happen in steps in time, or can they be happening at the same time, or without giving you time variables?
Well, most of my talk, I just assumed that the skeptic was making his bet all at once. So this is basically this equivalent. But actually it is more general because so if skeptic fixes a strategy for the game, that's equivalent to him making a bet all at once. It is true that he doesn't have to do that. He could bet as he goes along and have a new hunch every time and not have a strategy and so on. So when you introduce a sequential thing, you get something more general. But it's kind of like what I was talking about when I was saying, the scientific community makes one bet, and then you can make another bet, and there doesn't have to be a kind of strategy set out in advance. So this Q2 here can have nothing to do with Q1. It's somebody else's idea. There doesn't have to be some Q of Y1, Y2, such that this is the marginal for Y1 and this is the conditional for Y2 given Y1. You don't need that. You can kind of go by the seat of your pants as you're going along. So it does so this sequential element does mean that the betting picture is richer. But the nice thing about it is, one of the things that distinguishes between the Bayesian and non-Bayesian, the standard discussion about Bayesian and non-Bayesian, one of the elements is the question of a stopping rule. The Bayesian doesn't care what rule there was for when you stopped gathering information, because the likelihood ratio doesn't matter. But then if you do a non-Bayesian test, then it does matter what your program was. But here, if you're doing sequential things, it's like the Bayesian in that sense. You can do one thing and then decide to do something else. You can stop whenever you want. After you stopped, you can decide to keep going again because you're multiplying. It's like multiplying the likelihood ratio. It's a completely different theory, different motivation, different conclusion, but it has that same feature to it.
So your account is much closer to the Bayesian account than standard statistical testing. In this regard that you just said.
In this regard.
Also in that.
In this regard, but
alternative hypotheses. So it's not
yeah, in this regard, but it's not. It doesn't have the same. It doesn't have a Bayesian inclusion. Nothing like a Bayesian inclusion. That's important to remember. I've said it already, but I return to it. The fact that I end up with evidence 1,000,000 to 1 doesn't mean that I or any Bayesian would be prepared to bet 1,000,000 to 1 in favor of Q, because it might just be lucky that I multiplied my money by 1,000,000. But it's damn strong evidence. It's not.
Well, for the Bayesian too, it might not be willing to bet. Even though you have evidence of it, depends on other.
Well, it's not a probability. What I'm saying is not. It's nothing like that.
You have a name for your approach? Like the Atlantic City?
Game-Theoretic.
How about Atlantic, New Jersey, Atlantic City?
Atlantic City.
Well, my title of my paper is A Betting Language is a Strategy for Statistical Scientific Communication. Here, I'll give you another copy. I'm almost ready to put that on our website. I'm calling it working paper number 54, but I'm still gathering feedback, and I would welcome your thoughts for improving it.
So is there a right probability on this theory, or just kind of probability depends on the subjects?
Well, there's a notion here that what we're testing is a probability distribution that purports to describe a phenomenon.
Right.
The person testing it doesn't have to believe there's any probability distribution. He's trying to knock it down. He does have to believe there's an alternative Q that does a better job. He can believe there's no such thing. There's no probability distribution representing this phenomenon, describing this phenomenon. But in that sense, it's the idea that you're describing. I mean, so it's kind of Kantian, right? And whether that's objective or subjective.
So you say he doesn't have to think that there's an alternative. So that's the difference with the Bayesian account. Even if it's not an alternative probability hypothesis, the Bayesian still needs something about how likely the result is.
Yeah. Now the statisticians that try to do Bayesian things are not as, they're just using, often, I just comment that often they're just using it as a tool. The majority, I mean, Harry is, the other statistician in the room right now, he could give his perspective on this. But I think it's probably fair to say that most statisticians are not Bayesian. They're not dogmatic Bayesians. They don't really believe it. They use it as a tool. And they really.
I was just saying this because I'm not a statistician, but philosophers are all Bayesians as far as I think Deborah Mayo gave a talk here. She's the only one I know who's not.
Isn't it something? When I was young, it wasn't that way. You guys have really gone off the deep end.
Well, they're good. There are reasons for it, and
There's also reasons why statisticians aren't.
Right. Right, and that's so when someone who's a philosopher of science goes and looks and what statisticians do, they're sort of astonished. Bring the issue of stopping rules, for example. You're sort of astonished that they can think that makes a difference.
If there's a, like I return to, I mean, that's the philosophers should somehow grapple with the world as it is. There's 1 million people a year in the United States that think on this stuff.
We don't care about that.
How would you, do you think, is my characterization of statisticians accurate?
Not being Bayesian?
Yeah.
I think it's accurate. As I told you before today, I'm teaching Bayesian statistics this semester to PhD students. There's 10 students in the class, none of them are from the statistics department.
I've only, there was a time in my life when I was very interested in these questions, and I had a friend, maybe you know Roger Rosencrantz, who knows the word at all. Yeah, so I learned a lot from him. He was a Bayesian, he was a philosopher of science, but he took statistics seriously. And the impression I had then was that the Bayesians were sort of winning the battle over how there were big conferences. I even went to one in which I.J. Good was there, and I forget who else, but there was an argument over the Bayesians and non-Bayesians over how to make statistical inferences. And the impression I got was that the Bayesians were definitely on the outside, but they were winning the battle because they had reason on their side. And then I got interested in philosophy of physics more, so I haven't paid much attention. But I thought probably the Bayesian onslaught continued, and now lots of statisticians are Bayesians. I even knew a statistician who was basically Bayesian. His name was Bob Janner. But I just looked him up, and I found out that he became, instead he went into finance, and now I became really rich. He was a psychometrician, trained as a psychologist.
So the people that do Bayesian, there's a say like Bayesian society. What's the name of it? There's a
Probably the Bayesian, International Bayesian Society. I don't know.
Yeah, I think it has a journal, Bayesian analysis. You look at it, it's all about computation. They don't have anything interesting to say. Let's figure out how to do this.
Yeah, it might be that they have nothing interesting to say about how practicing statisticians should go about their work, but it still might give the framework in which you can assess how they're going about their work is correct or incorrect.
The main, well, maybe we're off topic, I don't know, but Harry and I have gone to a couple of these meetings of a group called Bayesian frequentist, who wants to bring people together. And the kind of...
With the fiducial people too.
Yeah.
I never understood what that was. Did they explain it?
Well, that's...
You don't have to answer.
I was just... I just wanted to give a general comment about what they're doing. The problem they face is that models have gotten so complex that there's no obvious frequentist methods. The sort of least-squares thing is a standard method, and for these very complex problems, they don't have standard methods. You can always do a Bayesian analysis, but usually the Bayesian analysis will be utterly stupid because you have no clue about what all these parameters mean and what putting a probability distribution on it does. So the Bayesian analysis is something that you can compute, but you don't know, it doesn't make any sense. So they're caught between having a theory that they're more comfortable with and a theory they can implement. So the fiducial method gives them a way of finding a Bayesian prior that might give good results, that will satisfy their frequentist desires. And that's why the three things come together. Like, that's my take on this one.
This is what they call kumbaya movement.
It isn't kumbaya, but the underlying belief is frequentist because they think they're trying to describe the phenomenon, not their beliefs. And also because the problem is so complex that starting with a Bayesian prior makes no sense because you can't understand what you're doing. I mean, so you'd like to give a uniform prior, but there's no such thing as a uniform prior. When you try to make a uniform prior, you're actually giving very high probability to some things you don't understand.
Sure.
So it makes
That's why
absolutely...
objective Bayesianism is so good.
But there's no way of giving a prior that is not uniform. I mean, there is no way of giving a principal one because you don't understand what these parameters are doing. It's beyond any working out. So what you do is you find a way of making them a prior that's not a real prior because the prior based on what the data is. So it's a phony prior.
It's an improper prior.
But that's not what an improper prior means. One that doesn't integrate to one.
Right.
This is improper.
But I mean, you might be forced to get one of those to satisfy. Have one of
That's
those
not
to satisfy you.
that's a minor problem. The real problem is your prior is going to be a data-dependent prior. It's a prior that you make up after you see the data. But it has when you use it, it has an acceptable frequency property. So the whole thing is driven by a frequency property, which is inevitable because you want to describe the phenomenon. You don't want to describe somebody's opinions. So these guys, these Bayesian statisticians, they're really not Bayesians. They're using Bayesian.
They're not Bayesian in philosophy.
Yeah.
They're using Bayes' rule.
Yeah.
And yeah.
They're not Bayesian.
But I think that the Bayesian, I mean, that maybe Barry would disagree with that idea. But I mean, the Bayesian
So the Bayesian rule
paradigm makes sense.
You need to understand what all these statisticians are doing. You need to understand it. So it makes sense for here to teach it. Yeah.
So, but you're saying that the journal contains basically just stuff about how to compute things, because once you have the rule is clear cut, right? You put a model, you calculate a posterior, but they can't calculate the posterior.
So that's
the whole problem.
That's the business of that.
But I guess then you just mentioned the problem of having to put priors on things.
What you said before reminds me of a quip that's attributed to hygienic glue. That's that you shall know your priors by their posteriors.
Yeah. So I thank you for listening to me, and if you, as I say, if you're interested, I can email you a copy of this document in its correct state, and in a few days I'll know available. I would appreciate feedback on the ideas and on the exposition. It's a kind of it's new enough. My collaborator, my co-author, and I talked today. I mean, he didn't quite understand what I was trying to say. So thank you.